You're looking live at the ILS Proton launch vehicle awaiting liftoff from Launch Pad 39 at the Baikonur Cosmodrome in Kazakhstan, with the Inmarsat-5 F2 satellite on board. Today's launch is scheduled for liftoff at 6:31 p.m. in Baikonur, which is 12:31 p.m. at Inmarsat headquarters in London, 7:31 a.m. here at the ILS Broadcast Center in Washington, D.C., and 4:31 a.m. at Boeing Satellite Systems International in El Segundo, California. Thank you for joining us. The countdown to the launch of Inmarsat-5 F2 begins now. I'm Karen Monahan, Director of Communications at ILS. Welcome to today's coverage of the launch of Inmarsat-5 F2, the second of 3 satellites scheduled for launch by ILS Proton to deploy the Global Express network for Inmarsat. We'd like to welcome viewers joining us from Inmarsat offices around the world. With me again is my colleague John Paul May, Vice President of Programs Operations and ILS Chief Technical Officer. John has worked on over a dozen launch campaigns from Baikonur and has co-hosted many of our launch broadcasts. John, welcome.
Thanks, Karen. It's great to join you here again in the Broadcast Center for today's launch. We're now about 14 minutes to launch, and the most recent weather readings we've received from the mission team at around T-minus 6 hours were sunny and clear skies, a liftoff temperature around -11 degrees C, which is around 12 degrees Fahrenheit, ground winds from the north and northeast around 2 to 4 meters per second. Upper level winds are within limits at all altitudes, and these conditions are within the Proton mission design for launch. Now, even in the most extreme temperatures, Proton was designed to withstand the year-round weather conditions at the Baikonur Cosmodrome. Here's a little more on that. Proton is specifically designed to launch in most weather conditions, such as extreme hot or cold. In fact, Proton can launch between -76 and +140 degrees Fahrenheit. In the middle of winter, the temperatures can dip as low as -25 degrees Fahrenheit at night, with the lowest temperatures on record being even colder. Temperatures can also rise to as high as 125 degrees Fahrenheit in the summer, with the highest temperatures on record being much warmer. The Proton handles these extreme weather conditions by controlling the environments inside the payload fairing and the use of underground storable propellants. When the Proton was originally developed in the early 1960s, it was designed as large as it is to discount weather as a factor for launching the rocket. Harsh upper-level winds are really the only weather condition that could cause a delay in Proton flight, and traditionally, in Baikonur, low upper-level winds are the norm. The ILS Proton mission design for the Inmarsat-5 F2 satellite will utilize 5 burns of the BRIZAM upper stage to place the spacecraft into a super-synchronous transfer orbit. Now, we engineers like to turn everything into acronyms, so we frequently refer to this mission design as an SSTO mission design, and will take 15 hours, 31 minutes from liftoff to spacecraft separation and insertion into the planned super-synchronous transfer orbit. Now, let's take a look at the Inmarsat-5 F2 mission profile.
The following is a description of the super-synchronous mission flight profile of the ILS Proton launch vehicle with the Inmarsat-5 F2 communications satellite on board. The first 3 stages function to propel the orbital unit into a suborbital trajectory. The orbital unit consists of the BRIZAM, payload adapter system, and the Inmarsat-5 F2 satellite. The sequence starts with the ignition of the powerful first stage engines that output 2.4 million pounds of thrust at sea level. As the ILS Proton lifts off from its launch pad, it immediately executes a roll maneuver to align its flight launch azimuth to 61.3 degrees in order to achieve a parking orbit inclination of 51.5 degrees as it travels in an east-northeast direction across Kazakhstan towards the Pacific Ocean. The engines fire for about 2 minutes, during which time the ILS Proton experiences maximum dynamic pressure. Then the first stage separation occurs. The second stage engines follow with nearly 540,000 pounds of thrust for 3.5 minutes, and then the third stage engine fires with 131,000 pounds of thrust for 4 minutes. The payload fairing is separated soon after third stage ignition, high above the Earth's dense atmosphere. At stage 3 separation, the orbital unit has traveled from Baikonur to Russia near the eastern edge of Kazakhstan at 51.5 degrees north latitude and is moving about 7,300 meters per second, or 4.5 miles per second relative velocity. The upper stage of the ILS Proton rocket is called the BREEZE-M and is designed to inject payloads into a wide variety of target orbits. There are 5 BREEZE-M burns in this SSTO mission design. The first BREEZE-M burn occurs about 1.5 minutes after the third stage separation, when the orbital unit is still in a suborbital trajectory. This will last long enough to achieve a low Earth circular parking orbit of 173 kilometers. This 4.5-minute burn spans from Siberia to Russia's east coast. 1 revolution and about 1.5 hours after the first burn main engine cutoff, the second BREEZE-M burn occurs. The resulting elliptical orbit is called the intermediate orbit and increases the apogee to 6,000 kilometers, the perigee to 295 kilometers, and decreases the inclination to 51 degrees. This 19.5-minute burn spans from the southern tip of the Japan island chain to 600 miles northeast of New Zealand. 2 hours, 14 minutes after the second burn, the third BREEZE-M burn starts. Soon after this burn shuts down, the depleted auxiliary propellant tank is jettisoned and the fourth BREEZE-M burn begins. The resulting orbit is called the transfer orbit, where the apogee is greatly increased to a supersynchronous altitude of 65,000 kilometers. These 2 burns add up to just over 20 minutes. During the coast phases, the BREEZE-M performs attitude maneuvers in order for the Inmarsat-5 F2 solar arrays to be exposed to the sun at a predetermined solar illumination angle, which is designed to satisfy its thermal and power requirements. 10.5 hours later, during the 5th and final BREEZE-M burn, the orbital unit will perform a large plane change maneuver from 50.5 degrees to 26.75 degrees inclination in a 3.5-minute burn. The 5th BREEZE-M burn and spacecraft separation occur high above Papua New Guinea. About 12.5 minutes later, the Inmarsat-5 F2 satellite is separated from the BREEZE-M to reach its targeted supersynchronous transfer orbit. The total mission time from launch to Inmarsat-5 F2 separation is approximately 15 hours and 31 minutes, and the total travel distance is approximately 3.5 times the circumference of the Earth.
Once the Inmarsat-5 F2 satellite completes its in-orbit testing period, the satellite and its 89 Ka band beams will provide flexible global coverage from its operational location in the geosynchronous belt. And we're just under 1 minute from launch. You can see it's a very crisp, clear day in Baikonur today. A little bit of snow on the ground, but overall a beautiful day for a launch. Long shot there of launch pad 39, where we conduct most of our commercial launches from, but we also do have a second pad that we use sometimes, launch pad 24. A little under 30 seconds. Should have a nice view of the Proton as it lifts off today. T-minus 15, and we'll listen to the Russian broadcast.
10, 9, 8, 7, 6, 5, 4, 3, 2, 1.
We have ignition. And we have liftoff of an ILS Proton from the Baikonur Cosmodrome in Kazakhstan with the Inmarsat-5 F2 satellite on board. About 10 seconds after liftoff, the vehicle does do a roll maneuver, which aligns the launch vehicle pitch axis with the northeasterly launch azimuth. Now the vehicle will soon experience maximum dynamic pressure, or max Q, which is the maximum aerodynamic stresses on the vehicle in atmospheric flight. And for Proton, max Q occurs around 1 minute and 2 seconds after liftoff and at a velocity of about Mach 1.6, and is sometimes accompanied by visible condensation if the atmospheric and lighting conditions are favorable. And here you can see it occurring now. We're just a little over 1 minute from launch, and we just went through max Q. Beautiful view there as the vehicle heads downrange, or we like to say in the rocket world, climbing up the hill. and everything seems to be proceeding nominally as the vehicle ascends over the Cosmodrome in a northeasterly direction and with a flight launch azimuth of approximately 61.3 degrees. About 90 seconds after launch, everything proceeding nominally. We'll have second stage ignition here in about 30 seconds. Now we're coming up on the first stage separation from the second stage, and that's set to occur at 2 minutes into the flight. And on clear days, observers will see a bit of a halo effect of light as the second stage engines ignite prior to the separation from the first stage. And we have confirmation of ignition of the second stage and a good separation from the first stage. And we have confirmation of planned level of thrust on all 4 stage 2 engines. And the second stage will operate for about 3 minutes and 27 seconds. The next key mission milestone would be the separation of the third stage from the second stage at L plus 5 minutes and 27 seconds. About 20 seconds after that event, the payload fairing pyros will fire, and that will separate the 2 halves of the payload fairing and jettison them from the vehicle. On a clear night with low humidity, I have observed the shutdown of the second stage of the Proton and ignition of the third stage of Proton. Lastly, as the ILS Proton travels northeasterly from Kazakhstan into Russian territory, our viewers will notice some brief planned time lags in our reporting of key mission milestones.
The Inmarsat Global Express will deliver seamless, globally available, high-speed broadband connectivity covering 98% of the world's population. Here's more about Global Express in this video provided by Inmarsat.
Global Express is the first high-speed broadband satellite network to span the world. Faster, more secure with unrivaled reliability, all from a single trusted provider. We've invested $1.6 billion to develop the most advanced Ka-band satellite service for land, sea and air. And how are we doing it? The first Global Express satellite is now live, covering Europe, the Middle East, Africa and Asia. The second will cover the Atlantic Ocean region, and the third, the Pacific. Global Express, powering global connectivity. Operating with a combination of fixed narrow spot beams to deliver those higher speeds and steerable beams so additional capacity can be directed in real time to wherever it's needed. It's maximum connectivity combined with maximum mobility, meeting the high-speed, high-volume needs of customers across aviation, enterprise, government and maritime. GX Aviation offers connectivity from nose to tail. Seamless coverage delivers cost-efficient, high-performance broadband. Fast, uninterrupted access to operational updates for crew, and the latest in real-time television, social media, and on-demand entertainment for passengers. Global Express drives operational efficiencies, enhances welfare and safety services for workers in the remotest regions. Oil and gas, mining and construction companies benefit from multiple broadband applications when in the field. Media users can transmit HD and SD live video. NGOs and aid organizations get the connectivity they need for emergency responses and to set up long-term development programs such as education and healthcare. For government users, Global Express is transformational, complementing the wideband global satellite network. Designed for global mobility, Global Express offers flexible connectivity on demand as a managed service or via steerable high-capacity leases, allowing cost-effective augmentation when needed. Supporting government personnel using mission-critical mobile applications. Fleet Express powers the smart ship revolution, taking operational efficiency to new levels. It delivers higher speeds through more compact terminals at a lower cost than existing VSAT services, while high bandwidth multimedia applications enhance crew welfare services. Fleet Express offers an unprecedented level of availability, integrating seamlessly with our existing fleet broadband network. We live in a digitally connected world, and we expect to tap into that world no matter where we are. Global Express delivers communications that go further, faster. One high-speed network, one trusted provider, one seamless global solution. Global Express, changing the future for us all.
We're now nearly 7 minutes into flight and coming up on some key mission milestones. So John, what can you confirm for us at this time?
So I can confirm that we have a good stage 2-3 separation and jettison of the payload fairing, and stage 3 is currently operating. The payload fairing jettison occurs at a relative velocity of 4,600 meters per second, or about 2.9 miles per second, at an altitude of 137 kilometers. Our next major milestone happens in just a few minutes, and that will be the completion of the third stage engine operation, which will be followed by the separation of the Breeze-M upper stage with the Inmarsat-5 spacecraft on board. So the Breeze-M is a restartable upper stage and is compatible with all major commercial spacecraft platforms for dedicated single and multiple launches. Let's learn more about the Proton technology and its role in the Inmarsat-5 mission.
Soon we will have stage 3 separation from the Breeze-M. The orbital unit, or the spacecraft together with the adapter, separation system, and Breeze-M, will be traveling at approximately 7,300 meters per second at the moment of separation, or more than 16,000 miles per hour. The Breeze-M will ignite for its first burn about 1.5 minutes later and will last about 4.5 minutes. About 4 minutes after the first main engine cutoff, or MECO 1, the vehicle is scheduled to go out of range of our ground tracking stations. After about 70 minutes, we will reacquire the signal prior to the second burn of the Breeze-M.
Okay, John, can you give us a current update on the mission now?
Yes, I just spoke to Baikonur, and we have confirmation of stage 3 shutdown, separation of the orbital unit, which is the Breeze-M and the spacecraft together, and start of the first of 5 Breeze-M burns.
Boeing 702 HP spacecraft provide new Ka-band global and high-capacity satellite services to Inmarsat, the leading provider of global mobile satellite communication services, and leverages Boeing's extensive experience in Ka-band satellite communication systems. Here's more about the manufacturing of Inmarsat-5 F2 in this video provided by Boeing.
Since the launch of CENTCOM in 1963, Boeing has developed many different families of satellites, the largest of which is the 702 HP platform. By comparison with CENTCOM, which was roughly 3 feet across, the 702 HP, when fully deployed, has a tip-to-tip span equal to that of a Boeing 737.
Our design is leveraged off the 702 technology that we have 21 spacecraft in orbit flying right now and 9 more in production in the factory. And similarly, we have a lot of experience on the Ka-band payloads. Over the last 20 years, we've been involved in developing Ka-band systems.
The Inmarsat-5 Global Express system will deliver mobile connectivity of up to 50 megabits per second of broadband data and communications. Each satellite has a pattern of fixed beams on the Earth, augmented by steerable beams that allow Inmarsat to address capacity hotspots as they arise.
The beauty of Boeing and the development of the Inmarsat-5 program is that it's all really happening under one single roof in El Segundo. So a lot of suppliers produce hardware for us, but it all gets integrated into the integrated satellite factory.
We have a great team, a combined team. Boeing and Inmarsat have worked together developing this complex system.
What I really like about the program is getting a chance to work with the Inmarsat customer and leveraging the technology that we've established over many, many years.
It's exciting to have partnered with them to develop this very powerful and capable satellite.
As John has indicated earlier through communication with the Baikonur control room, this is the point in the mission now where the Breeze-M is just getting started. A total of 5 burns will be required before we get to spacecraft separation. So John, do you have a current status on the mission at this time?
The communications center is reporting that the mission is nominal, and the orbital unit is traveling along the planned flight path. And I do have confirmation that the main engine cutoff of the first of 5 burns has completed on time. A few minutes from now, the BREEZM, along with the Inmarsat-5 F2 satellite, will enter a planned communication blackout period. And this is when the vehicle is out of range of any of the designated BREEZM tracking stations. The mission will be back in communication after the second burn of the BREEZM is complete, about an hour from now. And at that time, the BREEZM will download its stored telemetry data, which will be routed back to Moscow and Baikonur.
So, John, can you tell us what happens with the satellite after Proton completes its job and puts the satellite into its transfer orbit?
Well, our broadcast takes us through the first BREEZM burn, and after the broadcast completes, the BREEZM will execute an additional 4 more burns before separating the spacecraft into the planned super-synchronous transfer orbit, and that'll be 15 hours and 31 minutes after liftoff. The ILS Proton will have completed the mission of transferring the satellite from the surface of our planet into orbit. Inmarsat and the contractors will then take over telemetry, tracking, and control of the satellite from that point forward. The satellite will then execute a series of planned operations over the next several days, which include solar array deployments, antenna reflector deployments, and a series of orbital maneuvers. These maneuvers will decrease the orbit inclination to 0 degrees, raise the perigee, and decrease the apogee, which results in a circular geosynchronous orbit over the equator. Following a period of testing, the satellite will operate in geosynchronous orbit with flexible global coverage for Inmarsat and its customers.
You can keep current on the Inmarsat-5 F2 mission by visiting the ILS website, which is ilslaunch.com, the Inmarsat website, inmarsat.com, by following us on Twitter, or by liking us on Facebook. Also, at ilslaunch.com, you can check out pictures of the current as well as the past missions, read blog posts from the ILS mission team, and view past liftoff and broadcast highlights and full broadcasts. I'd like to thank John Paul May for co-hosting the broadcast with me and for all his mission updates.
Thanks, Karen. It was a pleasure, as always, to co-host the first ILS Proton launch of 2015 with you.
So this concludes our live coverage of the ILS Proton launch of Inmarsat-5 F2 satellite for Inmarsat. On behalf of all of our teams and our partners and customers worldwide, we thank you for watching.